Thanks very much. Yeah, I'm very happy to be here. So this talk is on MiniBoone's cross-section program, and hopefully it'll be a kind of good break between the nice talks we heard yesterday on the accelerator program, long and short baseline, and the nice talks from this morning on the theoretical side of the cross-section calculations. So this is a motivational slide, even though maybe it's not too necessary to stress here. So why are we interested in performing cross-section measurements with our neutrino experiments? The key argument that's always honed in on is the importance of understanding our energy reconstruction and obviously our rate measurements for neutrino oscillation measurements. That's something we're very familiar with and obviously is key, as was shown yesterday, to developing a strong and robust oscillation program. Another important aspect is beyond the oscillation program, the experiments that we're running or planning on running have very enticing beyond the standard model physics programs. And these beyond the standard model physics programs also rely on a good understanding of our neutrino rates, which means good models for those. If they aim to kind of be sensitive to potential new processes, you need to make sure you can convince people that you understand your intrinsic neutrino backgrounds well, and cross-sections clearly play an important role there. And just an example that I'll touch on in a few points during this talk is MiniBoone's recent low energy X results, where cross-sections play a big role in getting to those results and the interpretation of them, which is something that Ornella highlighted in her talk yesterday. So again, what I'll focus on is the cross-section program for MiniBoone. And this slide is basically just trying to summarize that it's a very broad program with lots of measurements and lots of interesting kind of takeaways and next steps. So what you're seeing here is just a kind of screenshot of different extracted cross-sections from our currently published results, which span different channels, different beams, different neutrino flavors. So I'll try and give a flavor of what these results tell us and what's next for this measurement campaign. So here's an outline for the talk. I first want to just specifically try and give a sense for why MiniBoone has an important role to play in neutrino scattering measurements, and specifically how we're taking advantage of the liquid argon technology to make relevant measurements for the field. I will then present the cross-section results that MiniBoone has produced so far and what we've learned from them. And I'll try to finish with some broader impact for these measurements and what comes next. Okay, so what I want to start with, instead of just kind of a generic overview of the detector, I just want to jump right into kind of what matters here from the experimentalist side, which is the detector observables. And really key in on the fact that the liquid argon time projection chamber technology allows us to, in some sense, step up in terms of what we can measure and therefore what we can learn from neutrino interactions. So here you see one of my favorite MiniBoone events. It's a fairly complex event, long muon, proton, and 4 electromagnetic showers from the decay of 2 pi zeros. So what matters here is how well we can measure all these things that are happening in the interaction. And to give a sense, our electromagnetic showers, we measure their energy to kind of 10–15% resolution with few degree angular resolution. Our muons, we measure their energy through range, which gives us few percent energy resolution. When they're exiting, we can use other techniques, which give us order 20% resolution. And about half of the muons in MiniBoone exit the detector. So we have kind of half of our data set is contained with few percent resolution, half of it is exiting. And here too, we have a few degree angular resolution on the muon. A really critical part of making kind of advanced measurements is measuring the protons in these interactions, part of the hadronic system. And here we really are able to excel thanks to the detector technology. So let me first start with the visuals. You see here examples of events with final state protons. This is a single kind of few centimeter little isolated proton coming from possibly a neutral current elastic scattering interaction. Here's one of our charged current events with 4 final state protons clearly visible. And here's one of our NUI interactions with the electromagnetic shower and a nice little proton. And the key takeaway here is that with the millimeter spacing resolution we have, we can detect protons, measure their multiplicity up to kind of tens of MeV kinetic energy. And that's really key to being able to kind of learn more about the hadronic system in these interactions. And you see here examples from some of our papers, measurements of their kinetic energy for the nu-e sample, and efficiency as a function of proton momentum for one of our analyses from the past generation of results from a year or so ago. So how do we get to being able to make use of this data? There's two parts to this story. One is the detector itself. Here you see the detector being transported to the detector hall at Fermilab in the summer of 2014. I'll just highlight two aspects of the success on the kind of operational side. One is the good argon purity that we obtain, which in turn allows our electrons to drift cleanly without being stopped along their path as they reach the electronics for about a couple meters. Are designed for like quenching over the full detector volume was kind of like a 50% level quenching, but we basically see almost no quenching, again, due to the very high argon purity, which in turn means uniform detector response, and therefore kind of improved calorimetric energy measurements. The other point I'll highlight is the fact that we've operated stably for 5 years, which gives us a huge data set of neutrino interactions and is overall just a big achievement for the technology, even for kind of experiments coming down the line. The other important side of how we got here is developing analysis techniques to make use of this data. So here I just have a few examples that show kind of demonstrations of E-gamma separation, our pi-zero mass reconstruction, how we get rid of our cosmic rays in our analyses, and use of calorimetry to tag protons. But really, these are just highlights. We have a long, long list of publications, which keeps growing on developing analysis techniques that allow us to make use of the data to extract interesting measurements from it. So what I've gone through so far is kind of getting a sense for what detector observables we can measure, why we can measure them well with this technology, and the fact that we've developed tools to really translate those images into kind of proper measurements of kinematics. So let me spend a couple words saying where our neutrinos come from. This is an aerial view of the Fermilab Accelerator Complex. There's Wilson Hall there. The key takeaway is that MiniBoone sits on two neutrino beams, both the booster neutrino beam line on axis. It was placed there in order to investigate the MiniBoone low energy excess. But we also sit, though off axis, with exposed to a fairly large flux of neutrinos from NUMI. So let me just give a few words on each of these and their characteristics, each of these beams and their characteristics. So for the booster neutrino beam line, as I mentioned, we're on axis. The mean energy of the beam is about 0.8 GeV. So we're kind of dominated by sub-GeV neutrinos. And it's primarily a muon neutrino beam with less than 1% nu-e contamination. And again, we sit on this beam line to kind of follow up on the MiniBoone observation. In this beam, we've collected about 500,000 mu interactions, which are what we're studying for our cross-section program. And so far, it's the highest statistics sample of neutrino-argon interactions, and one of the reasons why it makes the analysis we can do exciting. The NUMI beam is one we talk less about, so let me say a few words here. Obviously, the beamline itself serves Fermilab's long baseline oscillation program. We had a talk on NOVA yesterday. MiniBoone sits off axis with respect to the beam. So what does that mean for the neutrinos we actually see? Here you see the log scale flux we're exposed to, and it's definitely a weird shape for this flux. There's no real peak here. If you kind of look at the median energy or the mean energy of neutrinos that we have, they're actually on the order of 1 GeV as well. So for MiniBoone, NUMI neutrinos mean order 1 GeV, very similar to the booster. So that's not what you think of generally when you think of NUMI, but that's what it means for MiniBoone. And again, the distribution is actually this kind of falling exponential. Another key interesting aspect of being so off axis is the fact that we have kind of a fairly uniform mix of neutrino and antineutrino. And a very cool bonus that comes is that we have a fairly large electron neutrino contamination. It's not sub%, it's several %, which means that there's more neutrinos there for us to try and measure, again, for cross-section purposes. So when you take these two beamlines together, and the fact that we've run for about 5 years, this leads to a point I've made already, which is we have lots of beautiful neutrino interactions that we try and study. And here you see a selection of kind of different topology, different final states, and kind of all different types of processes where there's interesting things to try and key in on and provide measurements for. So just before jumping into the measurements themselves, let me say a few words related to the analysis or kind of generic aspects of MiniBoone analyses that are relevant. One is detector modeling and calibration. So making sure we can do a good job calibrating our detector is key to extracting measurements from it. I'll highlight two key aspects that we need to take care of. One is accounting for distortions in the electric field that comes up in the detector due to basically the buildup of positive ions from all those cosmic rays that are coming through. These lead to order tens of centimeter distortions if not corrected for. If we want millimeter resolution, we obviously need to do a good job taking care of those corrections. And the other one is signal processing. So we have these great wires with kind of high signal to noise, but the signals that they produce are actually fairly complex. And we have to do quite a bit of work to process those signals in a way that produces kind of clean, crisp images to then study. And kind of these developments and others are what allow us to have nice plots of our pi-0 mass with good energy reconstruction and good calorimetry, for example, to look at stopping protons, as you can see in the image here. Detector modeling also implies, kind of has consequences on systematic uncertainties due to our detector modeling. And there's a lot of information in this slide. What I'll just key in on is the fact that we've really made significant improvements in our detector modeling, and it leads to concrete effects in our measurements. So these are two plots for showing the fractional systematic uncertainty from different effects on kind of the same analysis, but with the older version and the upgraded version. This is a charge current N proton 0 pion measurement. You see this dashed purple line, it's detector uncertainties, and they sit at about 40%. So large uncertainties from the detector. This is kind of from 2018, 2019. The current version has that line sitting at 10% or below. So we've really made significant improvements thanks to the calibrations I mentioned in the previous slide, dropping our systematics from detector and kind of bringing them more in line with the uncertainties on the flux or the cross-section uncertainties from, for example, the backgrounds in this specific cross-section measurement. And this is what obviously helps us push the boundary and make sure our measurements become more and more relevant and meaningful. Okay, so now let me jump into the cross-section results that we've produced so far, try to summarize them and maybe give a few takeaways from what we learned from them. So what are we trying to do with our cross-section measurements? We're trying to enrich the available measurements, the measurements that are available for neutrino interactions, and specifically provide much needed data for neutrino interactions on argon. When we do so, we try to provide information in a way that is useful to the broader community to both build models and generators and just learn from kind of where things might be going wrong in order to improve in the future. And finally, but importantly, these measurements serve a purpose for our own interest. They are a foundation for our broader physics program, searching for beyond the standard model physics, as I mentioned early in the talk. So let's start with our inclusive measurements. I have here two of these results. On the left, I'm showing our kind of first key high statistics cross-section measurement, which is a double differential inclusive cross-section measurement for muon neutrinos, charge current muon neutrino interactions in the lepton kinematics. This is still using order 10% or 10 to 15% of our data set, and kind of really, I think, got us started in the cross-section program. On the right is the most recent inclusive measurement for muon neutrinos, which was just accepted to PRL a few days ago. It's a one-dimensional measurement, but it pushes a little bit the envelope in terms of what we measure. It starts looking on the inclusive channel at the hadronic system for inclusive muon neutrino interactions. What we're moving towards is looking at higher statistics measurements. Again, this is 10% of our data. This is like 3% of our data. And using that to go to even higher dimensionalities, such as eventually three-dimensional measurements of the cross-section. To first order, we see that on inclusive measurements we see areas where the models maybe are not doing so great, but overall the picture is not too dire. But I'll comment more on that when we look at the exclusive channels. The one thing I want to highlight here is that, or let me start over. In addition to inclusive measurements for our mu-neutrino interactions, because of that NUMI beam we sit on, we are also able to produce measurements for electron-neutrino cross-sections. The statistics are still not huge. We're statistics limited in this measurement, but it's a very it's a really good step in the direction of kind of making concrete measurements of electron neutrinos on argon. The first one, if you might be familiar, was a differential measurement from argonute at higher energies as a function of the electron angle. What we're looking at here is measurements as a function of the, again, kinematics of the electron. So the electron energy and the angle with respect to the beam. And again, here to first order, what we see is when you look at inclusive final states, or when you look at an inclusive measurement, our data and the various generators that we have access to seem to talk to each other at least. What we're looking forward in this frontier moving forward is starting to look at exclusive final states for electron neutrinos and performing analyses with the broader NUMI-NUI data set, which in the end will hopefully lead to about kind of a few thousand events measurements. So now let me move to exclusive final states, and let's start looking at what happens when we kind of start playing with protons. So here are our two measurements on this front. The left is a measurement of CCQE-like interactions. It's a 1D measurement. Here you see the distribution as a function of the cosine of the mu1 angle. And on the right-hand side, you see results as a function of the same variable where we're not trying to hone in on a specific interaction mode. We're trying to hone in a specific final state, which is n proton events without any final state pions. So as you can see, data Monte Carlo is not too bad, but when you get to that most forward-going bin at low momentum transfer, things are maybe a little bit problematic. So this is really kind of the lesson that we're learning here is once we start going into more and more exclusive final state, or maybe looking at higher dimensionality measurements, we really start to kind of running into issues with some of the models. But in some sense, it's good news. It allows us to learn where things are breaking down, and therefore gets us asking the questions, how do we make progress on this front? One thing to look out for is we are kind of expanding the range of final state processes we're looking at. So for example, we're working on measurements with no hadronic activity, so just the muon, for example, or events with 2 protons. That's another analysis we're working on. And importantly, we're looking at a kind of more diverse range of variables. Something that's very active in the community right now is looking at these transverse kinematic imbalance variables that try to kind of hone in on information that can lead to kind of understanding specific effects due to final state interactions or kind of isolating in different regions of your phase space specific interaction modes. Again, to try and understand better, where do I see disagreement? What models might be responsible for that in that phase space? Okay, the last exclusive category I want to talk about is pion exclusive final states. So right now, the only result we have published is in flux integrated cross section of charge current pi0 production. So these are events with a nice long muon. In this case, there's a proton, but we don't actually require that, and 2 electromagnetic showers that we construct to the pi0 invariant mass. So this first measurement was actually fairly early on in our cross-section program. It was published in 2019. I think what's most exciting here is kind of looking forward to the various measurements that we're working on, including first differential measurements in the pion kinematics for both charge current and neutral current pi0s, charge pion production, and kind of more rare and exotic interactions such as eta production and coherent pion production. And one thing I'll want to stress is Pi0 pion production, but Pi0 production in particular is very, very relevant to our BSM program because our BSM program is kind of a lot of the signatures that we're looking for in this program have to do with photons or electron-positron pairs. And obviously Pi0s are a big background, so we need to make sure we understand what that background looks like after trying to get rid of as much of it as possible. Okay, so let me now spend a few words talking about the broader impact of our cross-section results and future plans. So what I want to do is actually touch on a couple topics that came up in the discussions yesterday in some of the talks. So the first thing, and they really relate to kind of how we make use of our cross-section measurements, or even just the cross-section expertise that we get by looking at our neutrino interactions for our broader physics program. So the first thing I want to talk about is our Gini tuning effort. So our low energy access results, which were released last fall, were kind of one of the key pieces of them was upgrading our Gini version to Gini version 3. So we got this brand new release of Gini, which was great. It comes with a lot of bells and whistles even from a technical side in terms of, for example, assessing systematic uncertainties and so on. But what we wanted to do was really try and benchmark this model with some data. And what we ended up doing was actually kind of identifying some key model parameters that we wanted to tune to external data in order to kind of increase somewhat the robustness of the model and just have it talk to data before we use it for these exciting analyses. So what we did, we chose 4 parameters having to do with quasi-elastic and mech processes. The reason why we focused on these processes and not, for example, resonant pion production is because really the goal here was making sure the model was kind of doing a good job in the low energy region where, again, this low energy access search was really focusing its attention. And we took the model, these 4 parameters, and tuned them to data from T2K from a pionless charge current mu measurement. And here you see just a snapshot of one of the bins in this double differential measurement. The data points are the T2K data. The blue dashed histogram is the Gini model out of the box. And the red line is the Gini model after tuning on these 4 parameters. Now, these 4 parameters kind of are trying to model 2 different specific interaction modes. I'd say to first order, what is the result of this tuning? To first order, the result is we've essentially increased the normalization, and you can see that from the blue histogram going up to the red one, to bring better agreement again to this external data from T2K. And what we saw is that when we translated this tune to then comparisons with our own data, which obviously is an important cross-check we want to do as a step in this process, we indeed started seeing that good agreement in normalization for our inclusive mu-neutrino measurements. So here you have examples from all the from the 3 electron neutrino measurements in this low energy access search for inclusive interactions as a function of reconstructed neutrino energy on the top, inclusive interactions as a function of the muon cosine theta in the middle, and the CCQE analysis, so comparing to CCQE like mu interactions. Oh yeah, one thing I forgot to mention, but it's important. Why did we choose T2K data? Well, to first order, it's really the beam flux. It's sub GeV also. It's comparable to the one we're exposed to. So tuning to this kind of high quality pionless T2K data at sub GeV energies was in some sense the natural choice, but still a choice. And all this work is documented in a fairly extensive paper, which was accepted by Pierre a few weeks ago. The other point I want to highlight, which also was touched on yesterday in some discussion, is kind of further validations of the robustness of our model to kind of different, in some sense, unknowns in our interaction model. So we talked a bit about fake data sets yesterday in the context of the long baseline oscillation program. Before releasing the low energy access analysis from MiniBoone, we actually did something very similar. You see examples of fake data studies from one of our cross-section measurements here. There's a link to the supplemental material where this is described in detail. What did we do for the low energy axis analysis? Basically, we took sometimes 8 variations of the cross-section model, where some of the cross-section experts on the collaboration kind of got together and chose what should we play with, and they made some new Monte Carlo samples with these variations embedded. Those new samples were passed on to the analysis teams working on the low energy axis analysis. They analyzed them blindly. They did not know what was injected. And then we had kind of a revelation or presentations at the collaboration where the analyzers revealed the results and had to give kind of a quantitative assessment. Do I see some anomaly or not? And then we asked if that was consistent with what was injected in the fake data set. And then we discussed and discussed and discussed. But those tests obviously ended up working as they should have, giving us confidence in the framework we were using to make claims on the low energy access search we performed. The other aspect to this is sideband validation. So we have this tune of our interaction model. Before looking at different signal regions, we spent a lot of time looking at different sidebands rich in pi zeros, rich in charged current muon neutrino interactions. We looked at our nu-e interactions, particularly relevant to the electron neutrino low energy axis analysis. Basically, just trying to confirm as much as possible that wherever we looked in these regions, we saw agreement and importantly, kind of a consistency on a quantitative sense between the model with its uncertainties and the observation from our data. And this, I just wanted to highlight this topic in particular in the talk because this is really kind of, this would not have been possible without all the cross-section expertise within the collaboration, and really was a kind of several-month effort that kind of played a big role in our low energy access analyses. So let me spend a couple minutes on what's next. I'll give a generic slide and then touch on one topic that I'm particularly keen on. So what's next is, I'd say you should expect a couple very productive years from the collaboration. We've just collected our full data set. We now have mature analysis tools to analyze this data set and are working on a large number of kind of new measurements, looking at different final states, different variables to probe, different open questions that can hopefully help us make progress in building models and integrating them in our generators. Here's a long list of kind of different kinds of channels that we're looking at. I'm happy to talk about them in more detail. The one thing I'll highlight is that with all the legwork that we've done so far in developing our analyses, we now have kind of these nice samples of inclusive neutrino interactions, which we can then kind of break up into different variables, different final states. And really the reason I highlight this is because it actually makes the process of making these analyses somewhat more efficient. So hopefully leads to a fairly rapid turnaround with lots of results coming soon. So the one topic I wanted to touch on in detail was this kind of very low energy activity, something Ornella talked about in her talk yesterday. The reason I think it's interesting is because it says two things. One, there's more to look at than what we're looking at so far. And two, there's lots of room to further develop tools to make interesting measurements beyond the work that's already been done on that front. So the question here is kind of what happens to the nucleus beyond what we can already probe looking at protons, final state pions, and whatnot. For example, what happens to neutrons, what happens to nuclear de-excitations, things that are relevant both at the low energy scale, kind of tens of MeV neutrino interactions, but also at the kind of energy scales related to the accelerator-based program at the GeV scale. So what you see on the image here, this is an event display of some weird interaction in our detector. You can see this is a clear, nice proton, but some other weird stuff happening. And lots of these little blips, which are basically MeV or below energy deposits. So what you're seeing in the plot here is a distribution of basically the energy spectra of this low energy activity. The orange is showing you kind of the reconstruction that we use for all the results that I've showed so far. The blue is basically what we're developing. And you can see that we're able to, with improvements in our analysis techniques, push our thresholds to kind of order 100 keV or so in energy, which gives us access to all these little blips and therefore more information from the neutrino interaction. And yesterday, I think someone mentioned argon-39. So this is not really a measurement of argon-39, but you can kind of see this little shoulder here ending right at the right endpoint is, I'd say, likely coming from argon-39 distributed in the detector. This here is just kind of a shoulder from noise from other sources. So what we can do with these developments is basically build on the legacy from Argonaut. You may be familiar with Argonaut's result from, I guess, published in 2019, with looking for the first time at this low energy activity. And you can see here a nice takeaway from that result, looking at kind of the contribution to this low energy activity from nuclear de-excitations and neutron contributions. So we're really hoping to kind of build on this and continue this legacy, making really opening up this exciting area for measurements of kind of the nuclear recoil. And one thing I'll just highlight before ending on this topic is we just released a paper. It's an instrumentation paper related to measuring radon contamination in the detector, but it's the first paper in MicroBoone that uses our MEV scale energy reconstruction. And what we put that to use for is measuring basically coincidences of dipole coincidences where the alpha, even though highly energetic, 7 MeV, because it's an alpha, the charge signal is quenched significantly, leading to a very tiny blip of ionization, which we can nonetheless still detect and use in this case for this kind of instrumentation purpose. But obviously, now that we've developed this framework and are kind of able to deploy it for interesting cross-section measurements or measurements of neutrino interactions, rather. So I just want to touch on one thing looking beyond MicroBoone, and this is also relating to Ornella's talk. So MicroBoone is part of the broader short baseline program, which adds Icarus and SBND. Kind of the star of the show, once it turns on, will become SBND because it's so close to the target. As Ornella pointed out, it really means millions and millions of neutrino interactions, and kind of which means lots of exciting measurements on many different fronts. Things I'm particularly excited about with this program are kind of the rare processes that you'll be able to probe with good statistics. SBND Prism is as a concept, and on the detector side, the even lower thresholds for both charge and light compared to MicroBoone that SBND will bring to the picture. Okay, so let me now conclude. So just a generic conclusion, MicroBoone has a rich neutrino interaction physics program, many results already published with many more in the pipeline. Looking outwards, the goal here is to inform the community and provide data with which to benchmark and develop theories and generators. And looking inwards, our cross-section program is really critical to our own broader beyond the standard model physics program, as I hope I try to give a sense for in the talk. Okay, so thank you.
Thanks very much. Thank you very much for this very interesting and vibrant program. Yes.
Thank you. So, firstly, great talk, and it's great to see all this work coming out of MicroBoone. I want to make a comment on, I think it's slide 17, your PRL. So you introduced like your first few slides talking about identifying what you can measure in the detector. Mm-hmm. Just going to point out that true energy transfer is not one of those things.
Yes.
You have to go from the observed hadronic final state. You have to make an assumption about energy loss to neutrons, energy below threshold, the energy of the nucleus, right, in the initial state nuclear motion, and what happens in FSI, and all of that coupled to your detector efficiency to come out to this cross section.
That's right.
And so these comparisons, I honestly don't think can be trusted, because you haven't folded these through all of those things. You haven't corrected for the assumptions that you put in, extracting this cross-section using the one model used in your analysis. So I think, I mean, by all means, please tell me why that's incorrect. But the mapping between what you measure and true energy transfer is particular to your model and would be different for all of these. So, and you haven't done that.
So I guess, yeah, thanks for that comment. It's the first time we look at this, and I think it's worth debating and discussing, and it's fine to have that opinion. What I'll say on this is, where is it? So this is a topic. It's a PRL, so it's fairly short, but this is a topic that's discussed fairly at length in the supplemental material to this work. And it's true, it's not a direct process, and there's a significant amount of unfolding involved. And that is one of the reasons why, for this specific analysis, we went through this work of reproducing some of the fake data studies that had been with different models that had been produced in a similar way it was done for the low energy access analysis. So I agree. There's model dependence there, and it's a matter of addressing kind of to what level basically we tried ourselves to kind of throw at the analysis kind of challenges in terms of fake data studies with different models to see what came out from those, and they're documented again in the supplemental note. I think the kind of what the important follow-up is maybe discussing more generally kind of how useful is a measurement in this variable, or kind of are there other approaches that would be more useful to disseminate information from our data?
Well, I mean, I would say that everything you said in the initial 10 slides or so, saying identify the variables you measure and report in those, is exactly the way to produce a useful result. And I think that, you know, that is the opposite.
Thanks.
Well, yeah.
I wanted to ask about the MicroBoone tune with Genie version 3.
Yeah.
You mentioned there are 4 parameters which alter the amount of QE and 2P2H. Do you, I mean, do they move together? Is one less, one pulled less? What happens in effect?
They're to first order so there's the two that are most correlated are the normalization for the two, and they're anti-correlated, is what might make sense. Yeah. So beyond that, what I would say, I think what we've learned from this is that kind of we've tuned these 4 parameters together, but we have not done so in a way that I'd say kind of would give you. Let me start again. We've tuned the 4 parameters together in a way that allows, when we make inclusive comparisons, to overall get a decent agreement. But the takeaway should not be that we've now tuned these 4 parameters and our MEC model is doing a great job and the CCQE model is doing a great job. I think there, again, when you look at the individual interaction modes, we still see some issues that kind of will be working on in the next steps.
I had a very small clarification. On one of the slides, you said CCQE light and then CC 0 pi final state. Yes. And I'm not sure I understand the difference.
Oh, sure. So CCQE like, so CC and proton 0 pion is just asking what final state particles do I see? Let me tag them and select based on them. CCQE like tries to take advantage of the fact that we see both the muon and the proton and can use that information to kind of constrain the type of interaction mode we're in. So, but it still doesn't mean, as we've discussed, we all know there's much more going on there than just CCQE. But nonetheless, it is using kinematics information to try and constrain.
So you use, in one, you use the kinematical information to get ENU, while in the other you add a proton.
Yeah.
Okay.
So I want to ask, how well is known the cross-section for new muons versus new? You are showing that there is a problem to measure that apparently, or something like that. But how well is known at the moment?
So the difference between the two the new
Yes.
and new cross section.
Yes.
Yeah. So that's a great question. As you go to low energy, which we care about a lot, things get murkier. What I will say, what I'll say is that as our NUI measurements on NUMI get higher statistics, I think we'll be able to start making comparisons with our own data between the mu and NUI extracted cross sections, which will be interesting. Because in the NUMI beamline we have a good mix of both. We are also looking at making within the same beam ratio measurements of mu to NUI rates or cross sections, trying to, in some sense, take advantage of correlations between those. I don't think I can say too much on like what our deliverable might yet be in terms of either, how well we could constrain differences between the two cross-section models, because I think that's something we still need to study. But to first order, we're just starting to make use of the two data sets together, and we'll see where that leads to.
Okay, thank you.
Other question? Yes.
Thanks for the talk. I have a little bit of what may be a stupid question. So in this slide, you have this deficit in the forward direction, right? We also see a deficit in a lot of the low energy excess analyses, except for the one that doesn't have a proton. How do you know that in removing cosmics, you're not also scraping off events where the proton is overlapping with another object?
Where proton is overlapping?
Because here, I assume what you have here is a muon, and then when the proton is more or less in the same direction of that muon, that's probably where your angles are.
No, that forward-going bin is simply saying the muon is forward-going.
Okay.
So yeah, in fact, if anything, that's the region where there's basically no cosmic contamination because the muons are coming down mostly. So
the protons here may have all angles?
Yes. Yeah, so I'm not showing those distributions, but yes.
Okay. But the question is, okay, maybe the question is less interesting now, but how do you know that you're not removing these events when you remove the cosmics?
I'll say, what can I say? Two things. One, when we, well, how do we model our cosmics? Maybe that's a good thing to say. We do so in a data-driven way. We record data with the detector when the beam is off, in a way that's otherwise identical to when the beam is on. And then we simulate our neutrinos and kind of plop them on top of that data. So that models all of our noise features and the cosmic ray flux. I mean, it's modeled perfectly, it's data. So it's an entirely data-driven process. So in that sense, yeah, I don't, because of that, I don't really see areas where a mismodeling or a misunderstanding of our cosmic removal could really play a role. And in particular, I'd say in the forward-going direction. I think I'll leave it at that.
Okay, thank you.
Maybe we can follow up, yeah.
Thanks. Is there any other questions, comments? Yes.
So a couple of things that maybe we can then continue them offline. So this tune that you guys just published.
Yeah.
So it's an interesting study case, right? So from the point of view of mechanics, right? So you take some of the Valencia model, and I think maybe some of the empirical Deichmann model, and then you add them with weights that are determined by experiment. Calling that theory-driven animates a lot of theorists. But what I'm saying is like, so let's take this an example of a theory that's something that you would like to like test or exclude, right? I mean, this literally on a priori on physics grounds, you would expect this to be an example of something that's not like very, very physically sound and you'd like to exclude it. So, so what are the prospects or what kind of program can one think in the next year or so where a scenario like that could be rigorously tested and maybe ruled out? You have to look at like specific details of hadronic final states or something like that. It's an open-ended question, but I'm curious, maybe there's already enough data to take something like that. You know, a crocodile where you combine it with a hippo with weights that are to be fixed by, you know, a fit, and then try to see if such a thing can be included. That's, you know, I don't know if people are thinking about this.
I think that's very attractive. And what we've, so in fact, something we've started, we haven't acted on, but we've started discussing, and I think would be very interesting to pursue, is kind of moving from this this method to like introducing pole terms for specific parameters in the models to either constrain them or, as you say,
basically you need some pools, and then you have to quantify that the pools are being pulled in different directions.
So I think that's something that I know there's been some discussion in the collaboration, and there's some groups interested in pursuing, and so it'd be interesting to, I agree, carry that out with the goal of kind of diagnosing more than kind of patching in some sense.
Right. And the second question about your energy reconstruction. You guys have an algorithm where you look at individual hadrons and you apply particle ID information in this, or is it?
Yes. Okay. It changes a little bit analysis to analysis, but to first order, if we see a proton, we tag it. If we see something and we tag it as a proton, we include its energy as a proton.
Energy as a proton.
Yeah. Awesome. The inclusive analysis does the same for the pions, if it can tell they're pions, and so on. Yeah.
So that's already better than Dune. So you can already tell them that this is an example that it works on real data.
Actually, an interesting follow-up. Let me just go to this. Where does that become an issue for us? This is from one of the older analysis looking at final state protons. You see the efficiency for tagging protons, it rises up, of course, as that proton kind of becomes visible, but then it falls back down. And in this analysis, that's tied to, I mean, the problem is generic. As the protons build momentum, it's more likely for them to re-interact outside of the nucleus. So it's a final state interaction outside of the nucleus. And that's, I'd say, a big challenge that we still have not really overcome. That would be interesting to, that would need more work. It has to do with both tagging the particle and reconstructing its full energy.
Other questions or comments? If not, let's thank David again.
Thank you.